Welcome everyone. In this video we will derive the remaining two kinematics equations. I say the remaining because in the last video I derived the first two of them, and using our results from that video we will make our derivations today. So if you haven't seen that video, please go ahead and do so. Now, in the last video we used some calculus to make our proofs, but in this video we won't need to use any calculus. We will be just using some algebra. We will be fine. So I want to write our proofs that we made on the last video. So one proof was to find an expression for the velocity at any time. So we call it Vt, and it turns out that it is equal to V naught, the initial velocity, plus the acceleration times time. Now you could put vector notations with putting arrows like this, but in this video I won't bother doing this, just to not occupy unnecessary space. But on the last video I did put the arrows, and they are there. These are vector quantities. So using this equation which we proved on the last video, I want to derive an expression involving final velocity, initial velocity, acceleration, but I don't want time. So I want to derive a time-independent equation. All right? And before doing that, I actually need to give the other equation that I derived. So this is for delta x, the displacement, and this is as follows. V naught times time plus 1 over 2 a t squared. And don't forget, the acceleration is a constant. And I want to put the arrow just to specify that both the direction and the magnitude of our acceleration is constant. So how can we use these two equations to derive a time-independent equation? Well, to do that, let's just square this first equation. Let's take the square of both sides. So v square vt, and we get v squared. And notice I will name it with a subscript f. This just means the final velocity. Maybe you are interested at the velocity at time equals 10. It is your final time, so it gives you your final velocity. So this is Vf squared. Well, on the right we have V naught plus At. So if we square it, we get V naught squared plus 2 V naught At plus A squared T squared. Here, if I were to factor out, let's see, what shall we factor out? If I were to factor these two terms as 2a maybe, yeah, 2a would do it. If I factor out a 2a here, let's see what will happen. We will get v naught times time, plus we will have a 1 over 2, right? So that 2 and 1 over 2 will multiply to give us 1. We will have a remaining a, then we will have a t squared. Well, look at this. Does this look familiar to you? I mean, I guess it does. It's right here. It is our formula, our expression for delta x, the displacement. Well, it's great. So if we write our result, we have v final squared is equal to v naught squared plus 2a delta x. And boom, look at this. Do you see any time term here? Well, you can't see it because there isn't any time term. This is time independent. So this means that even if you don't have a stopwatch in an experiment, if you are able to measure, one of these quantities, and there are 4 quantities, this, 2 is just a constant, obviously. If you measure some of these, you can be able to figure out the others without ever needing to use time information. So this is great, and it is called the time independent kinematics equation. This is a really neat equation, and you will encounter this a lot. It is very helpful. So we did one of our proofs, and there's one remaining. Now the second proof, the second derivation that I want to make is to express delta x, the displacement, in terms of time and the average velocity. All right? So we have delta x, and I want to relate it to somehow time and the v average. Alright, this is all great, but how can we carry out this proof? How can we find a formula for the average velocity? Well, I claim that it makes sense that v average would be our initial velocity plus our final velocity divided by 2. I mean, this makes sense, right? I claim that this will be the case, but let's see if my claim holds. So, and of course, if I were to, this makes sense, I think should make sense to you. If we multiply v average with time, we should get delta x. We got this. So, my claim is, if I sum initial and final velocities and then divide by 2, I should get v average. So, let's see if that is the case. I am substituting for v average here. We have, and I want to make it in red, v naught plus vf divided by 2 times time. Well, great, but what can we say about v final? We have a formula for it right here, which we just proved on the previous video. So let's use that one. We substituted v naught plus at divided by 2 times time. Right, this thing inside the parentheses, that is just vf, as we showed. So this will give us 2v naught plus at, and if we distribute this t to the addition, we will get a t here and a t squared here, divided by 2, and we will get, if we divide by 2 both terms, v naught t plus 1 over 2 a t squared. And this sure is equal to delta x. We just set it right here, and we use that result even here. So it holds that v average is equal to basically the average of the initial and the final velocities, the mean of them actually. So our other equation is delta x is equal to v naught plus vf divided by 2 times time. In the past, I didn't really used to like this equation because I found it unnecessary, but you will see in some cases that this equation can really make things a lot simpler than using the other three. But as I said, if you don't like this, you don't need to use this. The other three will just do fine, but in some cases, this really helps a lot. So this is it for this video, and this is it for kinematics equations. I want to again emphasize that these 4 equations only work if your acceleration magnitude-wise and direction-wise is constant. Otherwise, you cannot use them. I hope this was helpful and hope to see you in another video. Until then, take care.